let me introduce my report. Mass-separated high-flux ion beam for fusion-oriented material research. Motivation of the problem. The economical efficiency of fusion power stations strongly depends on lifetime of first wall. The erosion of first wall, as well as other ion surface interaction issues critical for fusion program, are under intensive research. The ion surface interaction are investigated either in tokamak or using laboratory setup. While general trend in Europe is closing the tokamaks in favor for research founding, many laboratories have started to focus on fusion-oriented research of ion surface interaction and related material properties. However, modern laboratories aimed on material research face essential dilemma. The laboratories have to split their budget between tools for surface analysis and equipment which provides either relevant particle and heat flux. The tools for surface analysis are well known and cost of their ownership are well established. In contrast, equipment for steady state and high heat and particle fluxes has not yet been standardized and represents state-of-the-art device. Actually, there are only a few of them available in Europe, such as Magnum PSI, Pilot PSI, and Blade. There are only a few of them in Japan and the United States. Then a number of ion beam devices with magnetic mass separation available. However, typical ion fluxes are well below 10 to 12 particles per meter per second. Therefore, fusion community requires standard and affordable tool which helps to widespread fusion-oriented material research over small and medium laboratories. Its size and cost should be similar to ion beam sources. It should provide either relevant, steady-state ion and heat fluxes to the sample surface. It should provide continuous operation over many days to achieve high enough particle fluence. The typical properties of conventional anode layer thruster for space propulsion are the following. Satellite propulsion has to be compact and reliable in order to fit the space program. To drive the satellite, the space propulsion has to generate powerful and stable ion beam. Typical anode layer thruster provides the ion beam current in the range of up to 300 milliamps. Ion beam is steady state up to 200 hours of continuous operation, and its typical working pressure range is the following. So, converted and modified space propulsion could be used for fusion-oriented material research. The principal theme of anode layer thruster is the following. The construction provides A cross B field. There are electronic drift layer in this field, and the main ionizing processes occurs as this layer, and the ions are accelerated in the flux by accelerating voltage. To adopt the thruster for fusion research, it's necessary to convert cylinder type ion beam to cone-like ion beam. This conversion should increase ion beam current density. To implement the ballistic focusing, usual plain cathode and anode were replaced by this one to provide cone-like beam. After the ballistic focusing, it was proposed to use the magnetic system with reversible magnetic field. This new modification of the anode layer thruster has been titled Falcon and patented in the United States. To find out the trajectory of the ions in the Falcon ion source with the ballistic and magnetic ion beam focusing, the analog of the Bush theorem for paraxial beam and the energy conservation law were used. These calculations were performed for the following distribution of the magnetic induction perpendicular to the ion flux. The hydrogen ion trajectories in Falcon ion source are presented on this picture. This curve corresponds to 0.5 keV ions, and this curve corresponds to 6 keV ions. The ion energy distribution function was measured by a sector type energy analyzer. The resolution of the energy analyzer is 30 eV. The energies of the beam are spread over the range from 650 eV up to few keV of accelerating voltage. The strong magnetic field near the anode affects the trajectories of slow hydrogen ions, bending them towards the cathode. Therefore, low energy part of distribution function is cut off. The ion beam intensity was obtained via sputtering CO2 layers on C wafer via hydrogen and argon ion beam. One can see that the beam intensity is well concentrated within the spot with a diameter of nearly 3 millimeters. So, small beam spot provides high heat and particle flux, yet the cost of the pumping system remains relatively low. The sputtering coefficient of the hydrogen ions and such impurities as nitrogen and oxygen differs in near 50 times. So, a small percentage of impurities in the beam can significantly distort the result. It causes the necessity of ion trajectories calculation. Ions of different energies have different deviations in the crossover plane, in the beam crossover plane. And this picture shows the result of numerical calculation of ion trajectory deviation with taking into account experimental ion energy distribution function. One can see that the beam impurities are separated to form the circle with a diameter nearly 6 millimeters, more than 6 millimeters. And the central part of the spot is free of impurities due to magnetic separation. A set of experiments on high flux ion beam impurities mass separation was carried out. Cyclohexane was used as a working gas. Why cyclohexane? Because of its molecule dissociated at gas discharge. As a result, there are hydrogen ions presented in the beam and CH group ions presented in the beam. Polished stainless steel samples covered with TN were irradiated. The radiation experiment showed that impurities are separated and form the circle of radius from 0.6 to 1.3 centimeters. There is a free of impurities central part, and here we can see the spot of hydrogen ion beam. And I hope it works. There should be mood. Oh yeah, it works. We can see how the tungsten sample is placed on the super. It's moving about the application of Falcon source for fusion-oriented material research. And then tungsten sample was exposed to the hydrogen ion beam. And now we can see the ballistic and magnetic ion beam focusing in action. Ion beam radiation heats up sample in a few minutes. The focus in the beam decreases power density that leads to the tungsten temperature decrease. Beam is focused back and sample is heated up again. After the irradiation, we can see that before irradiation there were polished surface and eroded surface after the irradiation. And after the irradiation, the samples was examined using scanning electron microscopy. Fluence-dependent investigations was carried out during this experiment, and one can see the small part of lamina here. Conclusions. Falcon source produce particle flux above 10 to 20 power per square meter per second and up to 20 megawatt per square meter megawatt per square meter. This covers the radiation parameters range for plasma facing material almost entirely. Therefore, Falcon ion source is suitable for material research for ITER and future demo reactor. It could be used either for steady-state radiation or for combined steady-state and pulse irradiation of the samples in the following particles range. Most effects of low-temperature periphery of ITER plasma can be modeled with this KEV hydrogen ion beam. The key advantages of Falcon ion source are very compact size, affordability, intrinsic capability for impurity separation, and absence of redeposition. The long time of continuous operation allows for reaching the following fluency. The beam is focused into a spot of nearly 3 mm in diameter to reduce cost for pumping system. The impurity ions are separated to form a circle with a diameter of 6 mm. Therefore, the central part of the spot is free of impurities due to magnetic separation. Small volume of beam transportation makes the source suitable for investigation with hazardous materials. Falcon design is simple for maintenance and operation, makes it suitable for student scope. The result of my PhD thesis published in 11 scientific papers and presented nearly more than 20 different conferences. Thank you for your attention.
Thank you. Question?
Yeah.
All right, let's start there.
How do you diagnose purity of your ion beam? Like you said, you have a beam of 3 impurities, so pure deuterium or
Pure hydrogen or deuterium or tritium?
how pure? Is it 100% pure plasma, and how do you know this? And the first point, can you try mixed plasma or only non-biased?
Yeah, thank you for your question. Now I try to answer your question. This picture is shows us maybe the best that hydrogen is focused in this spot. If there were some impurities, 5% or smaller or bigger or more than 5%, they will be separated, and they will be on this circle, this circle, this circle, this circle. The more mass, the more diameter of the circle. So if you have some percentage of impurities, it will be on the edge of your sample, so the central part can be irradiated with pure ion beam, and this size of the spot allows all the surface diagnostics or analysis to view the results of irradiation.
So you use spectroscopy to measure this, right?
We used spectroscopy wasn't used during our experiment, but we used our wasn't used. Spectroscopy wasn't used.
You haven't tried mixed plasma.
Hmm?
You haven't tried mixed plasma.
Have we tried to mix plasma? We work only with hydrogen or mixture with hydrogen or argon as impurity, or the most.
Okay, more specific question. Deuterium helium plasma. Have you tried this acidic plasma? Have you tried deuterium helium plasma?
No. We have not experimental conditions for use tritium.
Not tritium. Deuterium helium.
Deuterium helium. It's suitable for using deuterium tritium, but we have no such working gas in our laboratory.
Okay. Anybody else have a question? Yes. Yeah.
Do you foresee the use of such configuration for example, Ethernet beam injector, maybe a cluster of Falcon instead of the classic multi-grid accelerator? And if you foresee this, what are the main advantages of this Falcon configuration based on the cluster with a node layer with respect to the
multi-grid? We have no grid, because of any grid should be replaced maybe some hours of operation. Yeah, the grid and source cannot provide such fluxes in steady state regime, as I know. We have no how to say, heated cathodes. Yeah, hot cathode. It's called cathode ion source, so it can operate as well with hydrogen as well as reactive gases, and the period of continuous operations should be much bigger in comparison with multi-grid ion sources.
Why much bigger? Because even in that case you have problem of heating, so in principle multi-grid accelerator can reach also steady state condition and working with several different gases has the same feature of the panel.
And
what is the point, the main advantage?
The main advantage is no grid, the simplicity of construction and the affordability. The resources are compact size. It can be placed in any camera. You should use only only two power suppliers. One supplier high voltage, and the second supplier which bears the magnetic field coil.
And that's the last question.
Okay, that's one.
Have you considered the presence of a ceramic channel because tracer with a layer is very similar to Oleksii tracer.
Oleksii tracer,
So maybe you can consider the use of a ceramic channel to even have better performance of the beam.
To use
A ceramic channel.
ceramic channel, yeah, no. The exciting construction without ceramic channel can reach can reach the fluxes and fluences. So we try to use it maybe in future, but that construction also can be used for amount of fusion-oriented material research without some modification or moderation.
Okay. Thank you. I think we should go.